Hello again. Last time we looked at the book, What is Man, Adam, Alien or Ape? We read the beginning of a chapter entitled Death and Taxes. Now, by that, I simply meant that only human beings worry about death and taxes. And we use that as a springboard for a comparison of human and chimpanzee behavior and lifestyles. And we moved on then to differences in anatomy and achievement. Basically, the purpose of this chapter is to show the vast difference between human beings and the great apes, among whom the chimpanzee is supposed to be our closest relative. Now, the whole idea of a close relative, or even a distant relative, is that there was at some time in the past a common ancestor from which both chimpanzees and human beings sprang. And that's what we're going to look at now as we continue our readings in this chapter. So we begin the section headed Uncommon Ancestors. The strange thing about evolution's common ancestors is that they are amazingly uncommon. Elusive might be a better word. The problem is a general one, which was highlighted in my 1978 book, From Nothing to Nature. You can draw a Darwinian tree of life that purports to show how all life forms have arisen from a single root via a trunk separating into main side branches and then into smaller branches and so on, terminating in a vast number of twigs on the periphery of the tree's canopy. But where on this tree of life do we find all the life forms known to us today, whether living species or fossil remains? Answer: as specialized organisms fully adapted to their environments, they are all located at the extreme ends of the outermost twigs. The multitude of alleged intermediate forms, which in theory populate the inner regions of the canopy and should be found sitting at every branch point, are simply not there. Every organism present in the modern biosphere or in the fossil record is a fully adapted life form, showing no signs of wanting to become something else. The alleged common ancestors are at best hypothesized and at worst unknown. To repeat, common ancestors are uncommon, to say the least. Let me illustrate this in relation to the alleged common ancestor of chimps and humans. A recent study published online in the Proceedings of the National Academy of Sciences is entitled Fossil Hominin Shoulders Support an African Ape-like Last Common Ancestor of Humans and Chimpanzees. The research, it says, suggests that the simplest explanation, that the common ancestor looked a lot like a chimpanzee or gorilla, is the right one, at least in the shape of its shoulder. An identity parade featuring nothing more than a suggested shoulder shape is, I submit, unlikely to produce a convincing candidate. So let's try again. A 2013 article in the respected online journal Phys.org offers a contrary theory. The last common ancestor of man and ape was not a knuckle-walking, tree-swinging hominid resembling today's chimpanzee, said a study, challenging some long-held theories of human evolution. Rather than a prototype chimp, as commonly believed, our common forefather was an ape, unlike any that exists today. The researchers themselves write, our reconstruction reveals that some Miocene apes represent a more appropriate model for the ancestral morphology from which hominins, that's humans and their ancestors, evolved than do living great apes. The last common ancestor, whose identity remains uncertain, most likely walked around on all fours like today's apes, but leaning on the palms instead of front knuckles. Notice that the common ancestor is unidentified. Its identity remains uncertain, say the researchers, and it is most likely that it walked on the palms of his hands. An online article from the University of California at Berkeley sums the matter up. The narratives of human evolution are oft told and highly contentious. There are major disagreements. Interpretations of almost every new find will be sure to find opposition among the experts. Disputes often center on diet and habitat, or whether a given animal could walk bipedally or was fully upright. What can we really tell about human evolution from our current understanding of the phylogenetic relations of hominids and the sequence of evolution of their traits? Hominid evolution should not be read as a march to humanness, even if it often appears that way from narratives of human evolution. The article goes on at some length to remind the reader that man really is just another ape, and implies that looking for a specific common ancestor is rather pointless. Certainly it offers no candidate for this attractive but unoccupied post. Quotes, where is the last common ancestor of human and chimps? Close quotes. I would love to know. That's quoted also. I would love to know, says Sergio Almatilla of the George Washington University in Washington, D.C. That question is keeping me awake at night. Subheading, Haldane's Dilemma. In the next chapter, we shall dig more deeply into the genetic similarities between chimps and humans. But there is one last matter that we must examine here. In 1957, evolutionary biologist J.B.S. Haldane published a calculation of the rate which evolution by classical neo-Darwinian processes should take place. Based on his assumptions, he concluded that it takes on average 300 generations of an organism for a novel version of a single gene, that is a new allele, to spread to all members of a colony and thus to become irreversibly fixed in the population. He wrote, the number of loci, that's genes, the number of loci in a vertebrate species has been estimated at about 40,000. Good species, even when closely related, may differ at several thousand loci. If two species differ at 1,000 loci, and the mean rate of gene substitution, as has been suggested, is 1 per 300 generations, it will take 300,000 generations to generate an interspecific difference. It may take a good deal more. This refers to a single interspecific difference, that is, a difference between two species. If we take 200 differences between chimps and humans discussed earlier and assume that phenotypic changes occur sequentially, this would mean 60 million generations, 30 million between the last common ancestor and chimps, and 30 million between the last common ancestor and man. Of course, if several different genetic mutations were being introduced at the same time, this number would be reduced accordingly. But it is widely recognized that such parallel changes in different genes rapidly reduce species viability as the number of such changes increases. Female chimpanzees usually give birth to their first offspring between the ages of 11 and 23 years. But let's be generous and assume that a generation among primates represents as little as 10 years. This gives 300 million years for the antiquity of the common ancestor, at least 20 times any conceivable evolutionary scenario. Simultaneous or parallel changes, if they occurred consistently, might reduce this by a factor of 3 or so. However, in this simple calculation, we are attributing each of the 200 differences between chimps and humans to only a single protein difference, which is obviously not true. For example, how many genetic mutations would be required to produce the upright stance and bipedal gait that is unique to man? Surely dozens, if not hundreds. We come to another subheading, the genetic waiting room. If you went into a surgery and found all the seats occupied by skeletons, you would conclude that the doctor had a waiting time problem. If Haldane is right, macroevolution is no more viable than the doctor's practice. Understandably, therefore, some biologists argue that evolution by random mutation and natural selection actually occurs far more rapidly than Haldane's calculation allows. One article even claims that, quote, no more than 238 fixed beneficial mutations is what separates us from the last common ancestor of chimps and humans, close quotes. Others, however, disagree profoundly. In a detailed research paper entitled "The Waiting Time Problem in a Model Hominin Population," John Sanford and co-authors used an established modeling computer program and generous assumptions for beneficial mutation rates to estimate the time required for genes to evolve by neo-Darwinian mechanisms. Note: hominins are a group consisting of humans and their alleged ape-like ancestors. Sanford and co-authors write, "We have focused on the waiting time problem as it would apply to an evolving hominin population of 10,000 to 100,000. Our numerical simulations consistently reveal that in such a population, the waiting time problem is profound. Even waiting for the fixation of a single point mutation is problematic. The waiting time for the establishment of such a simple event requires on average over 1.5 million years. This is a very long time to wait for such a tiny genetic modification of a pre-human genome. It makes us ask, is such a long waiting time credible?" Close quotes. And needless to say, even if there were only 238 mutations separating us from the alleged common ancestor, and allowing for a limited degree of parallel evolution, the timescale on Sanford's calculation would still be far too long, of the order of 100 million years, to allow a credible evolutionary scenario. Subheading: A curious fact. We shall have to leave the various protagonists fighting it out in their attempts to date the unknown common ancestor. Such a technical debate isn't going to be resolved in a popular-style book like this one. I really only want the reader to grasp one thing. The question of man's biological ancestry remains unresolved, in spite of the confident assertions of the evolution-friendly mass media. But there is one final curious fact. If humans and chimpanzees did both arise from a common ancestor over a comparable timescale, however long that time might be, and given that mutation rates in modern chimps and man are known to be the same, why is man so much more highly evolved, I put that in quotes, than his alleged cousin? In fact, if evolutionist Ian Musgrave is correct, the situation is even worse. He claims while we are around 240 genes away from the last common ancestor, we are around 594 genes away from the chimp, so that they have fixed about 50% more genes since the last common ancestor than we have. Most of the genes substituted are for immune and reproductive system genes, and only a handful seem to have anything to do directly with brain function. This can only mean that chimps have actually evolved from the alleged common ancestor 50% faster than humans. How can it be, then, that the last common ancestor was itself a great ape, and according to some anthropologists, uncommonly like a chimpanzee. There are only two possible answers. Either there was no common ancestor, or else chimps wasted their beneficial mutations on keeping fit and having kids. By contrast, man, while not neglecting his quotes, immune and reproductive system genes, close quotes, also used his smaller set of mutations to master fire, invent language, do cave painting, write music, learn mathematics, discover DNA, and build zoos to accommodate chimpanzees. Certainly, we can't blame this vast difference in mutational productivity on natural selection, since both chimps and humans grew up in broadly similar environments. Evolution is an endless source of wonder. Well, in the next session, we shall proceed to the next chapter, where we shall be looking at the genetic differences between humans and chimpanzees. Thank you.